Hi everyone, my name is Lingling Fan. I'm a graduate student in Professor Shanghui Fan's group at Stanford University. Today I'm going to talk about non-reciprocal radiative heat transfer between two planar bodies, published on Physical Review B. Thermal radiation is ubiquitous. In the far field, where the distance between objects is larger than the thermal wavelength, only the propagating wave transfers energy, and the power density is subject to the constraint of black-body limit. On the other hand, in the near field, where the bodies are separated by a vacuum gap smaller than the thermal wavelength, the evanescent wave can tunnel through the small gap, and both the propagating and evanescent wave can transfer energy. Consequently, the power density can significantly go beyond the black-body limit. Now we consider one of the most common constraints in thermal radiation, which is reciprocity. If you have a reciprocal emitter, the spectral absorptivity that light is coming from at a given frequency, angle, and direction, alpha, which is also noted as this heat flux density as 2 to 1, has to be equal to the spectral emissivity, E, which is also represented by the heat flux density as 1 to 2, at the same frequency, angle, and direction. It actually puts a fundamental constraint on many solar and thermal absorbers, as shown by this red panel of a solar absorber, as dictated by the detail balance. High absorptivity at a given frequency angle necessarily implies strong emission back to the sun in the same direction. Consequently, the detail balance gives an intrinsic loss mechanism for many of these absorbers. However, we emphasize that the detail balance is not required from the second law of thermodynamics, but rather comes from the fact that most of the materials are reciprocal materials. It would be a lot nicer if the emission doesn't have to go back to the sun, but instead can be rerouted elsewhere, so that you have a second chance of getting energy out of this thermal radiation. In fact, there has been a lot of theoretical work showing that the fundamental limit of solar energy harvesting efficiency can be significantly improved, going from 85% to 93% if you can break the reciprocity constraint. Therefore, in recent years, there has been emerging interest in exploring radiative heat transfer with non-reciprocal materials. Examples include the design of photonic structure for complete violation of Kirchhoff's law between this alpha and E in far-field thermal radiation, as well as in non-planar structures in the near-field regime that people have shown this persistent heat current in thermal equilibrium and this thermal Hall effect. However, there has not been a systematic study as how non-reciprocity manifests itself in planar systems. Here we developed a generalized analytical formula for two-body planar heat transfer, where heat flux density from body 1 to body 2 as a product of mean energy per mode at frequency omega and this photon tunneling probability. Heat flux density from body 2 to body 1 as 2 to 1 can be obtained by exchanging the subscripts 1 and 2 and temperature T1 to T2. The photon tunneling probability is represented by the reflectivity matrix on the surface of two bodies using the general reciprocity theorem, and this derivation doesn't assume any reciprocity, therefore generally applicable for either reciprocal or non-reciprocal systems and in both far-field and near-field regimes. Using this formalism, we address how the second law of thermodynamic constraints near-field heat transfer in planar geometries. This thermodynamic constraint states that in thermal equilibrium, the heat transferred from one planar body to another at each frequency and in-plane wave vector is unchanged upon interchanging the two bodies, regardless of whether the materials are reciprocal or not. We further address how reciprocity constrains heat transfer in planar geometries. We highlight the uniquely non-reciprocal aspects of near-field heat transfer that cannot exist in reciprocal systems. This unique signature of non-reciprocity is a breaking of the symmetry of heat flux density in some equilibrium between positive and negative in-plane wave vectors. And all these constraints can be formally proved. Now we numerically demonstrate our findings in two-body heat transfer systems with the following examples. First, we consider a reciprocal system consisting of two planar slabs of reciprocal materials as shown here in this figure. We set body 1 to have isotropic dielectric permittivity epsilon 1 as the dielectric function of a plasmonic metal that takes the Jude model form. We choose the permittivity of the second body to be anisotropic and have the form of this tensor shown here. This form resembles the permittivity of a magnetized plasma, except that the permittivity tensor is symmetric, and hence the material is reciprocal. We place a perfect electric conductor on the back side of both slabs. We compute the radiative heat transfer between two bodies at each frequency omega and in-plane wave vector k parallel along the y direction, as shown here in the figure, corresponding to S122 and S221 respectively. We see the symmetry between opposite in-plane wave vectors at each frequency and at the same temperature, as expected from this reciprocal system. Furthermore, at each frequency and in-plane wave vector, we have S122 equals to S221 at all frequency and wave vector channels, confirming the validity of the general thermodynamic constraint. We emphasize that these constraints are satisfied despite the lack of any mirror symmetry in the system. Bodies 1 and 2 are made of different materials, and moreover, the permittivity of body 2 is chosen to be anisotropic, such that each frequency and each k parallel are not equivalent. Now we study a non-reciprocal case, a system where body 1 remains the same in the previous example. However, body 2 has an asymmetric permittivity tensor, thus breaking the Lorentz reciprocity. The heat transfer spectra for this system are shown here. We see that the symmetry between these opposite wave vectors are broken. Hence, based on the discussions above, we have shown that this system can achieve non-reciprocal near-field heat transfer in planar geometry. And this term, furthermore, we can compare between these left and right figures, and we see that S122 and S221 are equal for all frequency and in-plane wave vectors, in consistency with the general thermodynamic constraint. This numerical example demonstrates that the general thermodynamic constraint is satisfied despite the lack of both reciprocity and mirror symmetry in the considered system. In an earlier paper by Rayleigh, it was shown that the radiative heat transfer between two bodies in thermal equilibrium is symmetric, even if the system is via a two-part non-reciprocal system, such as a Faraday rotator. This result is equivalent to the lack of signature of non-reciprocity in this case. In this talk, I extend the result and show that the detailed balance of heat transfer can be violated even between two bodies, provided that heat exchange can occur in more than one channel. We formally prove and exemplify the result for heat transfer between two homogeneous infinite slabs. As I have shown here, if we do a iso-frequency cut at omega equals to omega p, and only these negative ky channels can contribute to the heat transfer, so that a heat transfer between body 1 and body 2 can occur in one channel, where the inverse transfer occurs in a different one, and constitutes a persistent current loop between the two bodies. We show that the condition for this current loop is the violation of Lorentz reciprocity. To conclude, we studied the heat transfer in two-body planar system, and there exists a universal thermodynamic constraint. We can violate this Kirchhoff's law in a near field, and we also show that the persistent heat current in this two-body planar system, even in thermal equilibrium. I acknowledge my advisor and colleagues for their support and mentorship, as well as the funding from ARO. Thanks for your time and attention, and I'm happy to take any questions.